Hello class, today what we are going to talk about is congruence transformations. And basically what this is, one of the definitions of congruent figures is that two figures are congruent if and only if there's a rigid motion or a composition of rigid motions that maps one of the figures onto the other. And if you remember, a rigid motion is a transformation that does not change the size or the shape of the original figure. And if it doesn't change them, then they are the same size, they are the same shape, which is the junior high, elementary school definition of congruent figures, right? Same size, same shape. So what I am going to do, real quick, I am going to use some patty paper here. This is basically just a tracing paper that's been cut down into a 5x5 square, so it's nice and convenient. And I'm going to trace this one and show you that I can just use transformations. For example, I could just rotate it and then slide it over, and it matches up. It is congruent to this other one. Or I could take this one and I could just flip it, and it's the same thing there. All right, so this is a reflection, a flip, and a rotation with a little bit of a slide going in there, right? So it's just transformations, these rigid motions to get from one to the other, and they're congruent. Over here, however, not happening, is it? Not congruent. There's no way I could rotate this, no way I could flip it over to make the one triangle match with the other triangles. Not going to happen. All right. So there it is. Congruence transformations, they have to be congruent. Okay? And another name for a rigid motion or combination of rigid motions is a congruence transformations, because the image and the preimage are congruent. And so there it is. Rigid motion and congruence transformation, those are interchangeable terms. You can use either one, means the same thing. Now, we do have two theorems here. First, reflection in parallel lines theorem. If you have two parallel lines, K and M, and if you reflect a shape over one of them and then reflect over the other, it's the same thing as doing a translation. All right. So we have segment AB is reflected over line K to A prime B prime, and then reflected again over line M to A prime prime B prime prime. And we notice that's the same thing as if I just took segment AB and moved it straight over with a slide. We'll do this. There we go. And so it's the same thing as if I took it and just slid it over. There it is. All right, now there's a couple of things about this. Number one, the segment A prime is going to be perpendicular to both of the parallel lines. Okay, because remember, reflections are always perpendicular to that line of reflection, because the line of reflection is the perpendicular bisector of A prime, and this one is the perpendicular bisector of A prime prime, which means that the distance from A to A prime prime is twice the distance between the two lines. Okay, what do I mean by this? Let's show you that. So we don't know what this distance is. That's fine. We don't need to. We'll say the distance from K to A prime is X units. All right. And if this is X units and the entire distance is D units, then from A prime to M would be D minus X, right? And here's the thing. The reflection is the same distance on both sides of the line of reflection, which means the distance from A prime to the line of reflection is the same as the line of reflection to A. So this is also X. And it means that this part of the reflection over here, this distance, is also D minus X. And so what we have, the entire length of this would be X plus D minus X plus D minus X, right? Well, x plus x minus x, all those x's cancel out, and I am just left with the entire distance from here all the way through to A prime is 2d. So if I know this distance, I know the distance from one translation to the other. The other one we have is reflections in intersecting lines. So if they're not parallel, what happens if they're intersecting? So if lines K and M intersect at point P, a reflection across one line followed by a reflection across the other line is the same as a rotation around point P. So for example, we'll use the same one here. We have AB right there, and I'm going to reflect it and then reflect it again, but that is the same thing as a rotation. All right? Same thing. And here's the thing about that. The angle of rotation is 2x, where x is the angle in between the two intersecting lines. Okay? Always the acute angle, not the obtuse angle. Okay? So, for example, we see here this reflection. The line of reflection, again, it's going to cut everything in half. So the angle here, I'm just going to, right? This distance, this measure, and this measure is the same, and this measure and that measure is the same. So this angle is congruent to this angle is congruent to this angle. And so we see that whatever this is in between the two, we've got just as much on the outside, and so it adds up to double whatever the original is. All right. And so that is nice, that's useful stuff. All right, let's take a look at some examples, some stuff we can do with this. So on number 1 and number 2, we want to describe the congruence transformation that maps triangle, the pre-image to the image, maps one shape to the other shape. So in this case, triangle PQR to triangle STU. And what we're going to do here, I'm going to use my patty paper, just because. It wants to know which of our rigid motions, because remember, congruence transformation and rigid motion are the same thing. So what this wants to know is, how can we use a translation or a reflection or a rotation or some combination thereof to get from here to there? Right? Yeah, PQR to STU. So I'm going to use my patty paper so I can trace this and see what's going on. So there it is. Now I'm going to do probably some rotations or reflections, something along that lines. So I want to make sure that I have a point of reference. So I'm going to also trace in the origin. That way I can see exactly where things have been moved to. It helps. Now, obviously, I can't just do a translation. Not going to work. So we could try either a rotation or a reflection. Now, I'm not looking at this. Well, let's see. We can maybe do a reflection. Let's pick it up, match up my origin there, and we see not quite. Not quite. So maybe a rotation, because this is in a different orientation. So we can rotate it 90 degrees. So not quite the right orientation. Let's turn it again. There we go. Now we've got the same orientation, right? So I did two 90-degree turns, so that's a 180-degree turn, or a rotation of 180 degrees counterclockwise. Don't have to say counterclockwise because that's the assumed thing. And then we're going to move it down. Well, how far do we move it down? We're going to move it down to here. And another benefit of marking the origin on here, it went from 0 down to -5, so I moved it down 5 units. Right. So to describe my congruence transformation, I had a 180-degree rotation around the origin, followed by a translation down 5 units. And there it is. There's my description of how I get from here to there to prove that it is congruent. Okay, now what I would like for you to do, I'd like for you to pause the video and then see if you can't solve number 2. Alright, let's see how you do. First, I am going to trace, let's see, we're starting with polygon ABCD. Pay very close attention to the order I want you to do, because if you started with EFGH and you went there, you're going to be backwards. And so your transformations are going to be wrong. Okay, so I am going to mark my origin. Now let's see, how can we get that? Well, let's see. Can't just slide it. Guess we're going to have to do something else because it's not matching up. It's in a different orientation. So the question becomes, can we flip it or do we need to rotate it? All right. Well, the reflections are easiest, so let's reflect it. Just flip it over. And does it match the right orientation? Yeah, it does. Looks like we can just slide it down, so let's just move it down. And there it is. It works. So let's see, what did we do? We reflected it over the y-axis, and then we translated it down to, what point is that? That is 4 and, let's see, 1, 2, 3, 4, 5. So we translated it right 4 and down 5. All right. So first we had a reflection over the y-axis, and then we translated it 4 units down. Sorry, was it 4 or was it 5? 4 units right, 5 units down. And so that describes our congruence transformation, the composition of rigid motions that gets us from one shape to the other shape. All right, so let's take a look at 3 and 4. Determine whether the polygons with given vertices are congruent. Use transformations to explain your reasoning. So let's see here. First, we need to graph these in. Triangle ABC and triangle DEF. So let's plot that one. This is, notice it's got the and there in the middle. That's because this is 2 separate shapes. All right, don't put these in there and think they're the same thing. Okay, so I made a little bit of a mistake there, but that's okay. We can deal with it. So are these congruent? Well, we're going to use our congruence transformations. Can we get from one to the other using translations, reflections, or slides? Well, let's see here. It does appear to be a reflection. And it looks just right over the x-axis, right? We can check that. Everything needs to be the same distance on the top that it is on the bottom, right? So B is 1 unit above the x-axis, E is 1 unit below. A is 2 units above, B is 2 units below. C is 1 unit above, F is 1 unit below. So we're good, everything's the same. We could, of course, do it with patty paper. So flip it over, line up my origin, and yeah, we see same thing. So that's how we did this. It's just a reflection over the x-axis. And they are congruent, just a reflection. So we're good. Okay, now let's try the other one. All right, so first things first, we do need to graph this. And looking at this, we have GHIJ and KLMN. So we have 2 quadrilaterals here. First, GHIJ. And we need JK, KLMN. All right, so let's see. Are these congruent? Can I do a congruence transformation to get from one to the other? Let's see. So, looks like maybe a slide, maybe. So let's try G. G would go to N, and that is a translation over 1, 2, 3, 4, 5, and down 1, 2, 3, 4. So left 5, down 4. Let's see, does that work for J? 1, 2, 3, 4. and down 1, 2, 3, 4. So it doesn't work, does it? Because they have to both move the same for a translation. And obviously a reflection's not going to work because they're both facing the same direction. So you can't do a rotation. So if I can't slide it, I can't rotate it, I can't reflect it to get it onto that position, there's no congruence transformation that will work. And so these are not congruent. So not too bad so far. Let's turn the page and take a look at some of this stuff. In exercise 6 through 9, so just going through 9, let's see, K is parallel to line M, and we want to reflect line UV in line K, and then reflect line U prime V prime in line M. So these two are reflections. We started here, reflected over line K, then we reflected that one over line M. So a translation would map segment UV onto which segment? Well, if I just slid UV over, would it match up with V prime U prime? No, it's facing the wrong direction, right? It's got to go all the way over to the reflection of the reflection. So that would be U prime prime, V prime prime. So here's the question. Which lines are perpendicular to U prime prime? And it might help to draw in U prime prime. I want a straight edge here. So we're going from U to U prime prime, right there. That's the segment we're talking about. Which lines are perpendicular to that segment? Well, that is going to be line K and line M. Because if you remember, that was part of our definition stuff over here, right? Segment A prime prime is perpendicular to both. There we go. Segment A prime prime is perpendicular to both lines of reflection. And reflections always move perpendicular to the lines of reflection. Next, why is V prime prime the image of V? And we need to explain our reasoning on this. So, V prime prime, the name of it says that it's the image of V prime, right? Because it's the image of V. However, how do I know that this is the image of that? Because we have this lovely theorem down here, reflections in the parallel lines theorem, that says this is just a translation of that, which means A prime prime is the image of A because it's the translation of A. So we are going to say that this is good by the reflection in parallel lines theorem. Let's see here. If the distance between K and M is 5 inches, what is the distance from V to V prime prime? Well, let's see. Reflection in parallel lines theorem might help us out again with this. It says the distance from A to A prime prime is double the distance between the two lines, the two parallel lines. Which means the distance from V to V prime prime is double the distance from K to M. So if this distance from here to here is 5 inches, from V to V prime is going to be 2 times 5 inches, and 2 times 5 inches is 10 inches. Not too bad. Pretty easy stuff. So let's take a look at number 10. What is the angle of rotation that maps A onto A prime prime? So here we have two lines that are intersecting. And what we have a reflection across K followed by a reflection across M. So they're intersecting. Let's take a look at this. Reflection in intersecting lines. The angle of rotation is going to be double the acute angle between those two lines. So what is the acute angle for those two lines? 60 degrees. So that means this angle of rotation from here all the way through to there is going to be 2x, right? What x is this angle here? So we have 2 times x, and x is 60 because of vertical angles, right? congruent. 2 times 60. So that means our angle of rotation is going to equal 120 degrees. Just to refresh, if you reflect over two parallel lines, it's the same as a slide, same as a translation. Double the distance between the lines. If you reflect over two intersecting lines, it's a rotation, double the angle there. And anything is congruent if you can do a series of rotations, reflections, and slides, translations, to get from one to the other. Hopefully you found that useful, and I'll see you in the next video.